Okay, so the TCP header is kind of relatively larger compared to UDP header because it needs to have a lot of field values to provide reliable in-order delivery and all other guaranteed service things. So again, the port numbers are still of the same size. So source port number, destination port number are 16 bits each. So now TCP deals things at the byte level. So each byte is given a sequence number. So in case a byte is lost or something, we can track it using a sequence number of that byte and then retransmit the byte and so on. So each byte is given a sequence number in TCP. That's something important to know. So that is why you allocate 32 bits for the sequence number field. So that means you could have up to 2 to the power 32 minus 1 bytes sent out. Now also you may have to do some like when you see the options field, one application of the options is to, if you want to extend the sequence number. So in the sense that if you are now the sequence number value for the bytes don't really start from 0. So when you establish the TCP connection process, we'll see the details later, but let me tell that right away. So you start with, so each side has to agree on a starting sequence number. So every time you start a session, the sequence number of the first byte you send will not be a 0. It could be any random number selected from the range of 0 to 2 to the power 32 minus 1. And the reason we do that is for two reasons. One is if the same source destination machines are running multiple sessions for the same port numbers, then for each session you may send some bytes. So you don't want the bytes from one session to have the same sequence number with the bytes of the other session. So that's why you start with a random starting sequence number so that you can distinguish between the packets of the bytes coming from the different sessions. So basically you don't want two bytes the same sequence number in the internet trying to reach the destination. So if 2 bytes the same sequence number reaches the destination, then the destination may just keep 1 byte, one copy, and then drop the other. Even though they may have different information, if they have the same sequence number, then destination will just drop 1. So you don't. So you want the bytes to have different sequence number when they are roaming around in the internet. So there is a name for that called outstanding bytes. So outstanding bytes means the bytes that have been sent but not yet received during the internet. They're called outstanding bytes. And also as a security issue, the receiver could do what is called, what is the next byte expected. So the receiver will see the details again later, will keep track of, okay, I have received this many bytes so far from the source. So what is the sequence number of the next byte expected from the source? So the receiver will keep track of that parameter. So if someone like an attacker wants to do what is called hijack a session, if he is able to guess the next expected sequence number at the receiver side, then he could come up with a fake message that has that sequence number and send that to the destination, and the destination could accept it because it could also fake the IP address as if it comes from the original source. And we'll see that as a separate topic in the next module on network security. So it's called TCP session hijacking. So you don't want an attacker to be able to do that. So that's why you start with an arbitrary sequence number that's going to be difficult for an attacker to guess. So for all these reasons, it is possible that the sequence number field will round off, in the sense that, imagine each byte is going to have a unique sequence number. So even though it looks like you have 2 to the power 32 minus 1 possible values of sequence numbers, there's possibility that sequence numbers will round up. So that means it is possible that two outstanding bytes may mean to be assigned the same sequence number. So in order to overcome such scenarios, you can make use of the options field, and there are of course several other uses for the options field also. So for this issue, you could have what's called a timestamp that is also 32 bits larger. So you have for one particular timestamp value sequence number that is like you can have 2 to the power 32 minus 1 unique sequence numbers. Then for another timestamp value which is 32 bits, so you can have another 2 to the power 32 minus 1 unique sequence numbers. So the combination of the timestamp and the sequence numbers will make the sequence numbers kind of unique. So that way you have a larger space, a larger number of unique sequence numbers you can use. Now acknowledgement field is also 32 bits, so it is used like sequence number. So again, TCP provides reliable service, so the destination has to acknowledge back for the bytes it has received. Again, the receiver doesn't acknowledge back for every byte. So as I said, the bytes are put together as a segment and sent. And you may also wonder, before I continue, so for the sequence number, so one thing you have to also remember that even though you have for a sequence number for every byte, so if you send things as a segment, for which byte in the segment you include the sequence number here. So the rule is you include the sequence number of the first byte in the segment in the sequence number field of a TCP header. So if a segment has multiple bytes, of course it's going to have, so you include the sequence number of the first byte in that segment in the sequence number field. Similarly, in the acknowledgement, you include the sequence number of the byte, which means a corresponding segment that you want to acknowledge for. Now, again, since the message boundaries are not preserved, the more general way to look at acknowledgement is you specify in the acknowledgement what is the last byte that you have received in order. So you may receive say 1000 bytes and another 1000 bytes and so on, and but you may have some gap and may receive bytes that were sent after those missing bytes. So when you send an acknowledgement, you send an acknowledgement indicating, like if I say 5000 as the sequence number field in the acknowledgement, that means the bytes up to 5000 have been received in order. So you don't have to really acknowledge for every byte. When you specify a sequence number value for the acknowledgement, that means bytes up to that value have been received in order. Okay, so that's how you make use of the acknowledgement field. Now the header length is 4 bits, so similar to the IP header. Remember when I was talking about IP header, I said you have a minimum IP header and a maximum IP header length. So similarly here, TCP header, you have 4 bits and you represent things in 32-bit quantities. So each is a 32-bit quantity here. So again, this is one dimension, but for visualization, we're representing as a 2-dimension as rows. So the first 5 rows here are mandatory, similar to the IP header. So the minimum TCP header length is 5 rows, which is each row is 32 bits. So 5 times 32 bits, which is like 32 bits is 4 bytes. So 5 times 4 bytes is 20 bytes. So that's the minimum TCP header length. And the maximum TCP header length, you can make it from here. So there are 4 bits. So you could have all the 4 bits to be 1. So that's going to be 15 in decimal. So 15 times 32 bits, which is 4 bytes. So that is 60 bytes. So very similar to the IP header. So the minimum TCP header length is 20 bytes and the maximum TCP header length is 60 bytes. Okay. Now the flag field. So here you have starting from, so you see the byte number starts from 0. So 0, 1, 2, 3. Those are the 4 bits allocated for the header length. So starting from bit number 4 to bit number 15, you have the flag field. So that means you have about 12 bits allocated for the flag, but all the 12 bits are not used. So let me put it out here. So you have 12 bits for the flag, so the first 4 bits are not used, so use only the last 8 bits. So among this, the Next two bits after the first four bits are used for congestion control purposes. So they are called the ECE flag and the CWR flag. So ECE means explicit congestion experienced and CWR means congestion window reduced. Now I mentioned about this in the IP header module, so let us go through this in detail now. So I have a slide for this. So the routers in the internet may experience congestion as packets go through. So the routers have a queue in which they buffer the incoming packets and they then send out the packets on those outgoing link edges. Now if a router is experiencing congestion and it is receiving some packets coming from a specific source, it doesn't want to drop the packet right away because it is being congested. It wants the source to slow down. So the router will need a mechanism to inform the source. Again, you don't want to use ICMP for this because again you cannot slow down the source right away. It may take a certain time to slow down the source. So you don't want to keep sending ICMP request messages. And again, you don't want to add traffic to the internet because already there's congestion. So that's why you don't want to send separate ICMP messages from the routers. So you don't want you want to implicitly intimate or tell the source that there's congestion. So you don't want to add new packets to the internet in addition to what is out there already. So for this purpose, we have a mechanism. So we're going to go through that. So in the ICP header, we saw this ECT. So that is called the explicit congestion. Let me make sure the name. ECT means, or it should be called ECN. I don't know. Okay. All right. Okay. So in the IP header, you have 2 bits for congestion handling. Now they are called ECN bits, explicit congestion notification. Now if the 2 bits are set to zeros, that means the corresponding host that is sending the packet is not, or whoever is, like, it could be set by both the source or the destination. We'll see the slide there, but if whichever host sets it to be 00, that means the transport layer protocol running at that host cannot handle congestion notification messages. If the transport layer protocol running at the host can handle congestion, it could be set, the 2 bits in IP header ECN bits could be set as 01 or 10. So that is why it's called explicit congestion handling at the transport layer. Okay, so that's what ECT means. Okay, so let us go back here. So let us say the source, the transport layer protocol, could handle congestion. So in the IP header, you specify in ECT 01 or 10. So it could be one of the 2 combinations that could be set. So when a router sees that, you see why this thing has to be done at the IP header, even though the transport layer protocol is the one that can handle congestion. That's what you're specifying here. The routers cannot see the TCP header content. So the routers can see only the IP header. So that's why in the IP header, you specify whether the transport layer protocol running on that host can handle congestion notification. So when a router sees that in the IP header, the ECT bits are set to one of these 2 values, and the router is experiencing congestion at that moment, it will reset those bits to 11. So 11 means congestion experienced, or let me make sure the name is right. Yes, so congestion experienced. So the router could reset those 2 ECN bits to 11. That means the router currently experiences congestion. Again, the router doesn't include its own IP address or anything. In the IP header that is sent by the source, the router just changes those 2 bits for congestion notification to 11. That means some router on the path from the source to destination is experiencing congestion. So when the destination receives it and it sees that the ECT bits in IP header has been set to 11. Now also let me make sure because you are sending packets, a data packet, right, from the source to the destination. So it's going to have an IP header and the TCP header also. Now these two bits that we're talking about at the and the flag field values, the TCP header, they are the ECE bit and CWR bit, right? Which I just mentioned, the two bits. These two bits. Now the source, when it thinks everything is fine, it won't set those two bits, so they'll be set as 0, 0. So the router again cannot do anything to those two bits, so they're going to come as it is to the destination. So when the destination sees the ECT bits to be set to 1, 1, it's an indication to it's a notification to the destination that some router on the way is experiencing congestion. So it is now the destination's job to notify the source to slow down. So what the destination does is, the destination will anyway send an acknowledgement for this data packet. So in the acknowledgement, so again it has to have all the headers. So the IP header is set to ECT 0110. That means the destination could handle any congestion notification messages. And then the ECE bit in the TCP header is set to 1. That means explicit congestion experienced. So the destination is trying to now tell the source, because the source transport layer protocol, which is what is sending the data, could see this information in the TCP header. So if once it sees the ECE bit set to 1, right, the source could slow down. So that's what is going to happen. So the CWR is still set to 0, so it is, the acknowledgement now makes its way back to the source. So now that router which is experiencing congestion could see the ECT bit set by the destination to be 0, 1 or 1, 0. So the router could set the ECT again to 1, 1, telling that it is experiencing congestion. That's like a reconfirmation to the source that yes, some router is really experiencing congestion, and the ECE bit is not just set by the destination. Some router out there is experiencing congestion. So when the source sees both the ECT set to 1, 1 as well as the ECE set to 1, then it's an indication to the source that it has to slow down. So in the next data packet the source is going to send, it will set the CWR bit to be 1. So that means the CWR means congestion window reduced. So congestion window, later we'll see the details, is like the maximum amount of information that the source can send at a time without triggering congestion in the internet. So the source is going to really estimate the congestion window size. Okay, so there are some algorithms we'll see probably next class to estimate the congestion window size. So when the CWR bit is set to 1, that means the source is reducing its congestion window size. So it's going to send less information at a time so that it can relieve congestion in the routers. So when a router gets a packet, of course the router doesn't know whether the source has slowed down, because the CWR bit is part of the TCP header, so the router cannot know whether it is being slowed down or not. But so the router just forwards the packet, and the destination will see that the CWR bit is set to 1. Okay, so when the destination sees the CWR bit set to 1, that means it's an indication to the destination that the source has indeed slowed down. So the destination, when it sends the next acknowledgement, it doesn't set the ECE bit to 1, because if it sets the ECE bit to 1, it means it's a notification again for the source to further slow down. So it doesn't want the source to slow down even further. So, and if the router is kind of, since it's going to see a reduced load coming from the source, right, because the congestion window is reduced, and if that itself is sufficient for the router for the congestion to be relieved, it doesn't set the ECT bits to be 1, 1. So if the router is getting relieved of congestion with just this slowdown from the source, it will let the ECT bits to stay as 0, 1 or 1, 0. So that's an indication to the destination that the congestion window reduced is set to 1, and the routers forwarding the packet have not set the ECT bits to be 1 1. So the destination doesn't then anymore set the ECE bit to be 1. If the router here is not satisfied with the reduction in the amount of information being sent from the source and it wants a further slowdown, then it could set the ECT bits to be 1 1, and that's an indication to the destination that even though the source has slowed down, some router on the way wants the source to further slow down. So then it can set, the destination can set the ECE bit to 1 so that the source can further slow down. But if a router doesn't set the ECT bit and the CWR is already set to 1, the destination will then send acknowledgement like this, setting the ECE bit is not set, it is set to just 0, that's like a default value. So then the router on the way will just forward that packet because it's not experiencing congestion. Then the source sees the ECE bit set to 0. That means it's an indication to the source that whatever it has reduced is good enough for the routers to get the congestion relieved. So it will continue to send the same amount of information without reducing it further. So this is how the what is called the explicit congestion notification is done by a router telling the source as well as the destination about the congestion, and the destination can then tell the source to slow down and reduce its congestion window size. Okay. Alright, so that is about the use of the ECE and CWR flag field. So let me see. Okay, we'll stop for a minute here and just save this video.